Hello. In this video, we finish up the fourth section of Chapter 7 on exponential and logarithmic functions in James Stewart's sixth edition of calculus. And this one is a very useful section. The material in this section is going to be very helpful for you in finding the derivatives of complex equations. I quoted this, I copied this quote from Stewart. The calculation of derivatives of complicated functions involving products, quotients, or powers can often be simplified by taking logarithms. So this process is called logarithmic differentiation. And we're also going to talk about E as a limit. But let me go ahead and start with the steps. Maybe I should have put this as the first slide. But the way that logarithmic differentiation works is you take the natural logarithms of both sides of the equation, and then you use the properties of logarithms to simplify. Why is this helpful? Well, because things that are taken to a power, when you do the logarithm of it, the power simply becomes a 2 times something. And if you have something divided by something, and when you take the logarithm of it, it's the logarithm of the top minus the logarithm of the bottom. And when you have two things multiplied by each other, and you take the logarithm of it, then it's the logarithm of the first plus the logarithm of the second. And so you see this takes complicated multiplication, division, power stuff that would have required nightmarish power equations and so forth. It just would have been really, really long and difficult. By taking the logarithm of both sides, everything becomes nice and easy, and you can go home instead of spending the next 6 hours, trying to reduce everything and probably making errors along the way, unless you're, perfect. This just really simplifies everything. When you have things multiplied by each other, divided by each other, and taken to powers, taking the logarithm of both sides and then riding the wave, it's really easy. So you start by taking the natural logarithms of both sides of the equation. Then you differentiate implicitly. You differentiate both sides with regard to x, and then solve for the derivative, dy dx or y prime. Okay, so that's where we're going. I'll say it again in a second, but let's start with an example here. Let's say you've got this horrible equation. If you love math, it's a wonderful equation. Ooh, let's do it. Okay, but I mean, remember, if you were to do this the normal way, the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Can you imagine trying to simplify that nightmare? And then at the top, just taking the derivative of the top alone, the first times the derivative of the second times plus the second times the derivative of the first. I mean, it would be horrible. Logarithmic differentiation is like, never mind what I was thinking. Okay, so it involved marijuana. Okay, I've never smoked or inhaled. I just want to make that very clear. I have not touched marijuana in my life, to my knowledge. Okay, so let's take the derivative of this by logarithmic differentiation. Okay, so how's this going to work? Well, first I'm going to take the log of this side, which is very easy, natural log of y, and then I'm going to take the log of the other side. Okay, log of y, very easy. So how do I do the log? Well, remember, a power in a log becomes a coefficient. And then I'm just left with 2 natural log of sine x. See how easy that is? And then I'm going to add it to the natural log of the second, which is going to be the 4 is going to be a coefficient times the natural log of the tangent of x, and everything's great. And then I'm going to subtract it 2 times the natural log of the bottom. Do you see how easy? I mean, you should cry at this point. Oh, who invented this? This is wonderful, and it works. It's not a trick, really. This is a real thing. And so this is logarithmic differentiation. So now we take the derivative, the implicit differentiation of both sides. So what is the derivative of the natural log of y? Why, it's 1 over y dy dx. Again, very nice, clean, and easy from a previous video. Now, taking the derivative of this, Well, it's going to be 1 over sine of x. So there's the sine of x. And the 2 is going to stay in the top. And then, of course, we have to do the derivative of what's inside of it. And the derivative of the sine of x is the cosine of x. And there you have that nice little thing right there. Okay, so what are we going to do here? Well, remember, the derivative of the natural log is 1 over it. So there's the tangent on the bottom. The coefficient stays the same. And then dy dx of the stuff in the inside. What's the derivative of the tangent of x? Well, it's the secant squared x. See previous videos. That's just something to memorize, that the derivative of the tangent of x is the secant squared x. Minus, again, when you take the natural log of this, it's going to be 1 over the thing. And there's the 2 in the front. And then we take the derivative of this, which is 2x. So 2x times 2 is 4x. And you see how easy this is? This is like, okay, so now let's do a little hocus pocus. We do the hokey pokey and we shake it all about. Multiply both sides by y. Yeah, there you go. And all this is in parentheses. Let's just call the cosine over the sine the cotangent, because it is, right? Sine over the cosine is the tangent. So the cosine over the sine is the cotangent. It's fewer things to write down, okay? Right. And here, I left it the same and leave this the same. Okay, so we're good here. So now all we need to do is let's substitute back. Let's get rid of the y. Substitute this for the y, and we have, oh, that's horrible. Doesn't that look horrible? But it wasn't that hard. This is wonderful. Logarithmic differentiation is the bomb. It's wonderful. I mean, look at that. I did that. I gave birth to this answer. Me, little old me. And it was easy. So logarithmic differentiation is spectacular. So what are the steps again? First, take the natural logarithms of both sides of the equation, use the properties of logs to simplify, then differentiate both sides implicitly. What are we doing? We're taking the derivative, we're finding the derivative of a horrible equation, and then we solve for y prime, or we solve for the derivative. And there you have it. Okay, this is the end of this section. And so Stewart also gives you kind of what are the 4 basic cases of derivatives with relation to exponents and all about that base, Okay, so first of all, you might have a exponential kind of situation where you're taking the derivative of a constant raised to a constant. Well, the derivative of any constant is 0. So that's easy. Case number 1. Case number 2. Okay, let's say you're taking the derivative of a function raised to a power. Okay, again, fairly straightforward. We're going to take the b, the power. It's a constant raised to a constant, a function raised to a constant power. So the b is going to be up front. And then this to the b minus 1. That's just normal way of taking the derivative of something raised to a power. And then we're going to, again, have to take the derivative of what's inside, which is f prime of x. Okay. Situation number 2. Situation number 3. Okay. We now know how to take the derivative of an exponential function where a constant is raised to a function. Okay. And how's that going to happen? Well, this is going to come out of the front, right? And then natural log of a, which is something in the previous video we learned how to do. And then again, we're going to take the derivative of the function itself. That's case number 3. The final case is, what if we have something that's really kind of complicated, a function raised to a function? Then we're going to use logarithmic differentiation and simplify. So here we have the 4 kind of cases of situations where we are finding the derivative of some sort of a base raised to some sort of an exponent. Not that hard. Okay, that's a summary of where we are. So this section ends with the discussion of e, 2.71828, blah, 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 as a limit. How do we find e? Let's say we've got a little time off because of some pandemic or something, and we just want to sit down and find e to some incredible, to 100 digits, or something. Well, here's the formula. So e is the limit as n approaches infinity of 1 plus 1 over n, all raised to the n power. There you have it. This is the formula for finding e and expressing e as a limit. And since we have all this time on our hands, let's go ahead and show how this can be the case. Let's say that f of x is the natural log of x, okay? So the derivative of this natural log of x at 1 is 1. We know that because the derivative of the natural log of x is 1 over x, and dx, and dx is 1. And so as when x is 1, you have 1 over x, which is 1 over 1, which is 1. And so this is 1. Why are we doing this? Because it works. So let's take the limit as x approaches 0 of f of 1 plus x minus f of 1. Why would we do that? Because the limit as x approaches 0, so because the derivative of something is the limit as x approaches 0 of f of x plus delta x minus f of x all over delta x, right? And so if we're doing it for 1, x plus delta x, then it's 1 plus x minus f of 1 all over x. The x's are kind of confusing here, but this is basically what it means to find the derivative at 1. You know, that's what we're doing. Okay, so we know that for the function we're using is f of x equals natural log of 1. So we can go ahead and do the function thing here. So it's the natural log of 1 plus x minus the natural log of 1 all over x, okay? Because that's what f of x is in this case. So that leaves us with the f of x as x approaches 0 of, well, what is the, this is going to be 1 over 1 plus x, right? Actually, I'm getting a little ahead of myself here. The natural log of 1 is 0. So minus 0, bleh, that just goes away. So we have the natural log of 1 plus x, and then the 1 over x comes from this x in the bottom. So basically, by the laws of logarithms, the same, we can put this, normally we're taking it out, but we can put this 1 over x back in the football game as the power of this thing. So the 1 of x went from a coefficient to the power. And then, of course, this 1 is basically, we've already said that the answer is 1 at this particular point, okay? This is the same, pardon, I realized I was missing a whole slide. Okay, so let me resume, although no time has passed for you because you're in a relativistic kind of Godfather paradise. Okay, paradox, grandfather, never mind. Okay, so we take this bottom thing here, and let me bring it forward to this page. So 1, okay, hold that thought. E is the same as e to the 1, and we've said that this is 1, so we can do e to the all this schlock. Wow, isn't that something? Okay, stay with me. We can pull the limit out. Limit as x approaches 0 of e to the natural log of 1 plus x all to the 1 over x, okay, right? Now we can get rid of the e to the natural log. Remember, it all pulls out and it disappears. So that's the same as the limit as x approaches 0 of 1 plus x to 1 over x. Okay, that's all fine and dandy. That's one way to define e. E is the limit as x approaches 0 of 1 plus x over 1 over x. Now, what I can do is if I define 1 over x as n, then it becomes this, which is what we started off with. So 1 over x becomes n, and x becomes 1 over n. And then as n approaches infinity, because of course as x approaches 0, this approaches infinity. And so this is the nice and tidy, you don't need to know any of that stuff we just did. This is the nice and tidy way of defining e as a limit. You don't really have to do that because you can look up what e is, but this is it. And this has been the final video in section 7.4 of James Stewart's calculus textbook, which is on derivatives of logarithmic functions.